do we have any questions? Yes. I will also apply the same late submission policy for my second midterm and also the final. So just keep that in mind. When you're late for 1 to 10 minutes, you will be penalized for 10%, which is 15 points for midterm and 20 points for the final, if I remember it correctly. So do plan your time wisely. Yes. So all my midterms and finals will be online. It's going to be the same style. That's why this time I gave everybody extra time to get you prepared. Yes. I haven't posted yet, but it's going to be on Canvas. It's going to be under the module midterm 1, where you find previous exams and review materials. Any other questions? Yes. It's off the maximum, so it's 10%, which is 15 points. All right, so that's for the midterm. I'll have more information to you on next Monday, including the statistics of the grades. Anyhow, so first of all, before we get started for today's lecture, which is on periodic trend, we want to congratulate yourself a little bit in finishing quantum mechanics, because right now we have an understanding on the basic of quantum mechanics. So for this one, we have our Schrödinger equation. All right, so by solving the Schrödinger equation, we get the wave function for hydrogen-like atoms or one-electron atoms. So these wave function, these one-electron wave function are equivalent to atomic orbitals. And in order to extend our understanding, our quantum understanding for hydrogen atom into multi-electron atoms, we're using the orbital approximation. So in the orbital approximation, we're saying, let's just assume all atoms, whether it's multi-electron or single electron, the atomic orbital shape or the wave function all have similar shape as the hydrogen atom. And then you can just fill in the electron into those hydrogen-like atomic orbitals. So for that, we end up with shell model and electron configuration of multi-electron atoms. So today is going to be the last lecture, which we were just looking at single atoms. We're looking at the periodic trend, namely like how does like ionization energy, electron affinity change when we go over the periodic table. And starting from next lecture, we'll start to talk about chemical bonds. All right, so getting started. The first and most obvious trend we're interested in are talking about size of atoms and also ions. So we can use this equation, which is effectively the multi-electron version of that atomic radii, the average atomic radii. All right, so in this case, instead of just using the atomic number Z, we're taking consideration of the multi-electron effect or the shielding effect by using the effective core potential. And just a reminder, you can calculate the effective core potential using that equation. Basically, that's the atomic number, the number of nuclei, number of proton in the nuclei, minus the number of inner shell electron, minus 1/2 times the same shell electron. So if you think about it, by just looking at this equation, you can already get some information about the periodic trend. So this is the point, like, I hope you don't want to just remember these periodic trends, rather like try to understand where this periodic trend comes from. So a sample exam question for me is, for example, I can ask you to explain why we have the periodic trend that's given. So for example, in this case, if we look at the atomic radii and just think about it, when we're looking at this equation, this part, n is on the top, right? So electrons or electrons in atomic orbitals with larger n, principal quantum number n, we expect it to have larger atomic radii r. All right, that's just looking at the equation, we get that information. And then secondly, we look at the effective core potential. So that's on the bottom here. That means atoms with larger effective core potential, we're expecting it to have smaller radii. So how does it work when we're looking at the periodic table? So if we look at the periodic table, the number of the period, that gives you the principal quantum number n of your valence atomic orbital. So let's just use the first group as an example. We're just looking at the alkali metals here, right? So lithium is in period 2, sodium is in period 3, potassium in period 4, and etc. So we can write the electron configuration together. This should be really straightforward. It's just a noble gas configuration, and then it's just one s electron we're talking about. So for lithium, that's 2s. For the sodium, that's neon 3s1. For potassium, that's just argon 4s1. And chromium 5s1. All right, so here, these are our valence atomic orbitals. You can also plug in these valence atomic orbitals and calculate the average atomic size. I'll skip my calculation here, but you can practice it yourself. You just plug in the numbers there. And what we have is for lithium, the average atomic size, that's 6. That's in Bohr radii. For potassium, that's 13.5. For potassium, that's 24. And for rhodium, that's 37.5, I'm sorry. So, like what we expect, right? We have the principal quantum number n that's increasing. And we have the atomic radii increase along the period. All right, so that's going down the period. Next one, we're going horizontal, and we're talking about the change of atomic radii along the different groups. So the 3 elements we're interested here, let's just look at carbon, nitrogen, and oxygen, again, just as an example here. So carbon is in 4a, nitrogen 5a, oxygen 6a. We can write out the electron configuration. That's always going to be helium. Carbon, that's 2s2, 2p2. Nitrogen is helium, 2s2, 2p3. And oxygen is helium, 2s2, 2p4. I know our valence electron is actually including the p atomic orbital, but we can't really calculate the effective core potential for those p atomic orbital. So I'm just going to use the effective core potential for 2s as a quick demonstration. So for carbon, you can calculate that to be 2, 2.5, and then 3. And likewise, you can calculate the average atomic radii here. That ends up to be 3, 2.4, and 2. So this trend is a decrease trend. So my arrow is always going to pointing to the larger number here for this entire lecture, so don't get confused. My arrow is always pointing to the larger number. If it's increasing, that's green. Decreasing, that's red. So just as a quick summary, let me just copy paste that equation here. So what we have is an equation that tells you the relationship between your period, which is given by the principal quantum number n, and also groups, which is given by the effective core potential. So in this case, what we have is the size of the main group element will increase as the period number increases. So this is primarily demonstrated by the principal quantum number n. And then at the same time, we'll have the main group element in the same period. The size of these atoms will decrease when your group number increases. So this comes to the effective potential changes and shielding effects. Right. Do you have any questions before we move on? All right. And so far, we're talking about atoms with different electron configuration. But when we're talking about ions, the atomic size of the ions, effectively, we can have ions with the same electron configuration. So this figure is in your textbook. You can look at it a little bit longer and try to understand what it means. So in this case, I'm just going to highlight 4 of them. So oxygen 2 minus, F minus, neon, and then sodium plus. So all 6 ions here, and neon, all have the same electron configuration. If you write it out, it's just going to be, or equivalent to helium 2s2, 2p6. So say in this case, how do you understand the trend we're observing here? Because we see a clear trend, right? So all oxygen 2 minus has larger radius size, and sodium plus has smaller radius size. So if you think about it, again, the equation we're using is the same, right? It's going to be, the same equation here. But in this case, our n squared is going to be the same. Our L is also the same because the electron configuration is all the same. The only difference here is the effective core potential. And this one has to do with Z minus number of low shell electron minus 1/2 number of same shell electron. So in this case, again, the electron configuration is the same. So these 2 numbers are the same. But the atomic number Z is different for these 4 anions or atoms. So if we write out effective core potential, what we're having is oxygen has the smallest effective core potential because it has the smallest atomic number in these 4 elements. So likewise, what we have is an increase of effective core potential from oxygen all the way to sodium. And that explains why we have a decrease atomic size right? So it's everything is given in the equation. You just need to think it through and try to figure out what is the origin of these periodic trends. All right, so that's everything about the periodic trend of atomic size. See if we have any questions before we move on. Yes. Sure. All right, so let's move on to talk about our second periodic trend, which is the periodic trend of ionization energy. So before we do so, we've been talking about ionization energy several times. So I'm just going to go over it again and give it a clear definition in what is a ionization energy. So in this class, when we're talking about periodic trends, unless it's otherwise specified, we're assuming we're talking about the first ionization energy, i.e. 1. So ionization energy of an atom that's being defined to be the minimum energy required to remove an electron from a neutral atom. Or the other way to put it is this is the chemical equation we're caring about. This is my reactant, which is some gas phase atom. This is our product. We're forming a cation in gas phase and a free electron. So ionization, the first ionization energy is defined by the delta E of this reaction. Or if we put it on the energy diagram, we have starting point, that's our atom in gas phase, and the finishing point, that's our product, which is X plus the cation plus a free electron. All right, so this process from Xg to X plus the free electron, this is our ionization energy. And this process is an endothermic reaction. So every time we call it endothermic, we're saying this is a positive number. The delta G of this process is positive. It requires energy to remove an electron from a neutral atom. All right, so endothermic, just a new terminology that describes that process requires electron for it to take place. So qualitatively, you can think about larger ionization means you need more energy to remove an electron from a neutral atom. Or qualitatively, you can think about larger ionization energy means your atom is more likely to be chemically stable. It's not always true, it's just sometimes it's true. And we also talk about photoelectron spectroscopy to measure ionization of different atomic orbitals. So remember before we were just talking about the first ionization energy. That's the ionization energy to remove electron from the higher atomic orbital, the highest atomic orbital, to remove just one electron. So in the photoelectron spectroscopy, you can remove the ionization energy of different atomic orbitals, right? So there are slightly different in these two definitions here. And we went over these photoelectron spectroscopy of neon before, and this is a quick review on photoelectron spectroscopy. What we have is we gave the atom enough energy in form of laser radiation or just photon. The energy of the photon is given by E photon equals to h mu. That's rooted in the wave-particle duality of light. And then once the atom absorbed h mu or E photon of energy, it went over the ionization process, eject one electron with certain kinetic energy. And that kinetic energy is being measured in the photoelectron spectroscopy. So photoelectron spectroscopy is the experimental method for chemists to measure the ionization energy of electrons from different atomic orbitals. And because by using the Koopman's approximation, we can connect the ionization energy to the energy of atomic orbitals, right? So it's the same idea. As a product, that's X plus a free electron. And in the reactant, that's a neutral atom. And we're removing that electron from atomic orbital NL to infinitely apart. So n equals to infinity and energy equals to 0. So this process is the ionization energy, and the measured ionization energy of a given atomic orbital is roughly equals to negative energy of that atomic orbital. Just going to write it again. So on the left-hand side, we have the ionization energy that's being measured. On the right-hand side, that's the electronic energy of atomic orbital. All right, and N and L are just quantum number that tells you which atomic orbital it is. So quick review in what we were talking about before our midterm exam. All right, so that's the definition of ionization energy, and how does chemists actually measure ionization energy and how we connect it to the atomic orbital energy. So this is the relationship we're talking about. The energy of your atomic orbital is the negative of your ionization energy and vice versa. So with that in hand, when we're talking about the periodic trend of ionization energy, like what we had, we want to use a certain equation. So in this case, we're using the energy equation. So this is the energy equation that's given. You can use Bohr model or Schrödinger equation to derive the electronic energy of different atomic orbitals. We're abbreviated in energy of NL atomic orbital is roughly equals to negative effective core potential squared over N squared. And that energy has a unit in Rydberg. And this part we just went over. That's just the Koopman's approximation. So if we have this part, it's QM. This one is Koopman's approximation. That ionization energy of atomic orbital NL is roughly equals to negative electronic energy of that atomic orbital. And there are several things we know. First thing, with the period increasing, right? We know that larger period number gives you larger n. That's a principal quantum number. That's a very ugly n. And n is on the bottom of our equation. That gives us larger electronic energy of my atomic orbital NL, or when I say larger, I mean it's less negative. And since ionization energy is the negative of your electronic energy of that atomic orbital, that corresponds to smaller ionization energy. Right, so it's deeply rooted in the actual mathematical equation here. And if we draw out an energy diagram, say the question asks you which element, lithium or sodium, which one of them has larger ionization energy, can you use an energy diagram to demonstrate why that's the case? So what we can do is we can draw out the energy diagram. And here, when it's infinitely apart, right, so we have the cation, or X plus, and a free electron. So at that infinitely apart, my energy reference point is always 0 for both of them. But for sodium, that's neon, 3s1, where for lithium, that's helium, 2s1. So since 2s has a smaller principal quantum number n, so this actually you can calculate the number. I'm not doing a calculation here, but you might be asked to actually do that calculation in the exam. So the ionization energy of lithium from this 2s atomic orbital is in this red line, and my 3s atomic orbital here, that's a valence electron for sodium. That's going to be my blue line. So you can actually do the calculation and get the number for these lines. And what we're having here is the ionization energy of lithium. It's going to be larger than the first ionization energy of sodium. All right, so here we're just talking about the effect of the principal quantum number, and the equation we're using are these two equations. The electronic energy of your atomic orbital is negative effective core potential squared over principal quantum number n squared. Right, so that's the QM part. And then the ionization energy is roughly negative of that electronic energy of the atomic orbital. So that's along the period. That's talking about the effect of the principal quantum number n. We also have the ionization energy change along the group. So let me just write out that equation again. ENL equals to negative ZEF squared over n squared, ionization energy equals to negative ENL. So in this case, we know that larger group number will give you larger effective core potential, which leads to smaller or more negative energy, which corresponds to larger ionization energy. So if we look at the actual graph here, what we have on this figure is on the bottom, we're going down the periodic table, right? So the period number, when the period number is larger, is smaller, you get larger ionization energy. So that's what the red arrow is telling you. And then for this green arrow, we're talking about the effect of the group. What we have is we go from group 1A all the way to the noble gas. You have increase of your ionization energy, so that's a group. But if you take a closer look here, on top of these two dominating trends, we have two smaller wrinkles here. Namely, the beryllium and boron, we see a change. So the beryllium has a larger ionization energy comparing to boron, which is contradict to what we expect. And then nitrogen also have a larger ionization energy comparing to oxygen. This also contradicts to the periodic trend. So you're expected to know this exception and why that's the case. And we're going over that right now. So I'm just going to quickly pause here. So far we went over the periodic trend in the ionization energy, the definition of ionization energy, and how to use the general equation to tell you the general trend, right? So ionization energy is going to decrease if you increase along the period, and it is going to increase if you increase along the group. So don't try to remember these periodic trends. Try to actually look at the mathematical equation and understand why that's the case. So now we're talking about the exceptions in our periodic trend along the group number. So in this case, the first ionization of energy of beryllium, that's 9.5 electron volts. And the first ionization energy for boron, that's 7 electron volts. You don't need to remember it. But you want to know that this one, beryllium, that's in group 2. And boron, that's in group 3. And the origin of this exception in periodic trend, you can actually rationalize it by just looking at its electron configuration. So let's look at their electron configuration and the energy diagram. So on the left-hand side, we have the beryllium, that's helium 2s2. And for boron, that's helium 2s2, 2p1. Right, so what we have is for boron, we put 2 electrons, that's both in 2s. For beryllium, that's both in 2s. And for boron, we have one of the electron goes into the 2p atomic orbitals. So the idea here is that these atomic orbitals, if we look at just the 2s atomic orbitals, then yes, because of effective core potential, your boron might have a smaller 2s atomic orbital, a lower atomic orbital. But in this case, it has a much lower ionization energy because the outmost electron in boron is actually in the higher energy 2p atomic orbitals. And we discussed how does the shielding effect breaks degeneracy between the s and p atomic orbitals, and why p atomic orbitals always are higher in energy comparing to the s atomic orbitals. So in this case, because the 2p electron is the outmost electron for boron, the ionization energy for boron is much smaller comparing to that for beryllium. All right. So that's the first exception. Is we still have the effective core potential changing the relative energy of the s and p orbitals, but 2p is higher than 2s. So that's why your boron has a lower ionization energy comparing to beryllium. So that's our first set of exception that normally takes place when we're comparing elements in group 2A and group 3A. It's beryllium, boron, or magnesium, aluminum. So from group 2 to group 3. The second set of exception is between nitrogen and oxygen. So in here, nitrogen, that's in group 5. And oxygen, that's in group 6. Right, so the normal periodic trend is predicting oxygen to have larger ionization energy because of the effective core potential. However, in this case, again, if we write out their electron configuration, for nitrogen, that's helium 2s2, 2p3. For oxygen, that's helium 2s2, 2p4. Or if we put the electron in to my atomic orbital, for nitrogen, in the p atomic orbitals, all electrons are singly occupied. We don't have the electron pairing energy penalizing. But in the oxygen, we need to start pairing the electrons in my p atomic orbitals. And that's going to sacrifice on some electron pairing energy that's disfavoring. So what it means is in the oxygen atom, we have 2 electrons occupy the same 2p atomic orbitals. and that electron that's paired up is destabilized by electron pairing energy. So because this electron is being destabilized due to electron pairing energy, it is easier to remove this electron that's paired in your oxygen valence electron. All right. Okay. Do we have any questions? Yes.
How are the electrons destabilized when they both occupy two fields?
It's related to Coulomb's law when you have two negatively charged electrons in close proximity with each other. But I don't want to say it's just because of the electron-electron repulsion, because the reality is we're talking about electron cloud, right? So now we have two electrons in the same atomic orbital. They're just in close proximity to each other. And that penalty is called electron pairing energy. All right. So I left a practice problem. You can do it yourself, and you can find the answer in the annotated note. Basically, it's one of the way you can imagine the exam question to be like. One part of the exam question is, can you arrange the elements in order of the ionization energy and so on. You'll have more practice in the discussion worksheet in next week. All right. So I'm going to jump through to talk about electron affinity. So this is the third periodic trend we're talking about. So here, let's just introduce the definition of electron affinity first. It's somewhat related to ionization energy, but different. So if we look at it, again, we start from a neutral atom, X in gas phase. Now we're talking about that neutral atom gaining an extra electron and form an anion. All right, so that anion has a negative charge, has additional electron comparing to its neutral form. So this process is by definition electron affinity. Or if we draw it on the energy diagram, now we're starting from a higher point where your neutral atom and electrons are infinitely apart. All right, so the reason this one is higher in energy is because you're putting your neutral atom and then the electron infinitely apart. When the electron is approaching to form that anion, it will be stabilized by the attraction force from the nuclei. So this whole process, whenever you have this free electron, you would expect that to be higher in energy. It's the same thing in the ionization energy case. And then the process in forming that anion, in bringing that electron from infinitely apart to form that anion, that's our electron affinity. And the first electron affinity is normally a negative number, means this process is an exothermic process. Or when we say exothermic, we're saying this process will release energy. It's just one of the terminology we use in thermodynamics. Right? Endothermic, it requires energy for the reaction to take place. Exothermic, the reaction releases energy. But it is hard to experimentally measure electron affinity. Now we know the definition of electron affinity. Next step is how do we actually measure it experimentally. So it's really hard to measure it experimentally because we can't really get those gas phase anion measured very well. So in this process, and we don't have electrons, free electrons just anywhere around. So when we're doing the measurement, the chemist also introduced a new term called electron detachment energy. So these two terms are very similar to each other. They're the reverse of each other. So the electron detachment energy is defined by, we start from an anion, or looking at the energy required to remove an electron from the anion to form the neutral atom. So this is just the reverse reaction of electron affinity. So when say that's a reverse reaction, if I copy paste this energy diagram here, right? So we have this red one to be our electron affinity energy, which is exothermic. The reverse reaction is our electron detachment energy. And this process is endothermic. And this delta E is equals to negative. So these two are reverse process. It just this depending on where your reactant and product is. Yes. Right, that's a very good question. So the question is there a difference between ionization energy and electron detachment energy? So ionization energy, we start from neutral atom, and then we're removing that electron from the neutral atom. Where in electron detachment energy, we start from the anion. So our starting point have additional electron, and we end up in a neutral atom. So it's very closely related. And in fact, when people are measuring the electron detachment energy, they can still use the photoelectron spectroscopy to do the measurement. It's just by definition slightly different. All right? Okay. So that's the definition of electron affinity and how people measure electron affinity by measuring its reverse reaction, which is electron detachment energy. So in chemistry, normally when we're talking about electron affinity, we're talking about how easy it is when an atom is receiving an electron. So larger electron affinity means we're forming more stable anion. So naturally, the periodic trend of electron affinity actually overlaps with ionization energy. So here we have the electron affinity decrease with the period number and then increase with group number. And when we say decrease and increase, what we're having is a more negative the electron affinity number is. It actually means that atom has larger electron affinity. And then by definition, all your noble gas will have 0 electron affinity. They're happy, they don't want any more electrons. So this part is a little bit more qualitative understanding. All right. The last concept we want to talk about, we have 5 more minutes, is electronegativity. So electronegativity is actually a combination of ionization energy and electron affinity. What it measures is how likely an atom is attracting electrons. So this is slightly different from electron affinity. Electron affinity is more or less describes the stability of the anion. And the electronegativity actually describes how likely your atom attracts an anion, attracts an electron. There are 2 different definitions or 2 different scales, popular scales of electronegativity. We'll just focus on the Mulliken scale for electronegativity for this course. So what we have is En, that stands for electronegativity, Mulliken. That equals to some constant and then absolute number of ionization, first ionization energy plus the first electron affinity energy. So our electronegativity, at least for the Mulliken scale, is always a positive number. The trend for electronegativity is because it takes consideration of both ionization energy and electron affinity, so it's easier to think about it from the qualitative perspective. So in this case, what we have is if we're looking at the alkali metals or our group 1 elements, it is very easy for the alkali metal to lose an electron, right? It has a valence electron of S1. So we're expecting it to have a very small ionization energy. It's hard for it to gain an additional electron as well, because you start from the period 1 to gain an additional electron, you're sacrificing that electron pairing energy. So for alkali metals, we're also expecting it to have small electron affinity. So taking together, the alkali metals will have very small electron negativity, or we call these elements to be electron positive. Right. In contrast, if we move over to the halogens of the periodic table and just think it through, it is hard for the halogens to lose an electron, but it is really easy for the halogens to gain an electron to reach that noble gas configuration. So the result there is your halogens are having large ionization energy and small electron affinity. Or, in the other words, your halogens are expected to have large electron negativity or being electron positive. Electron negative, I'm sorry. So taking everything together, we have our summary trend. So again, I'm just going to use my arrow pointing to the larger direction. We first talk about the atomic radii. We have the atomic radii increase when the period increases. And then we have the atomic radii decrease when the group decreases. Right, so these are related to the equation we're talking about. The period trend is for the principal quantum number. The group trend is for the effective core potential. Then we have our ionization energy and our electron affinity. Both of them are going to increase against the group. And decrease against the period. The electronegativity is a little bit weird because it actually goes diagonal here. The easiest way to remember the electronegativity trend is you remember the fluorine is the most electron-negative atom you have, and it goes diagonal. So far for these periodic trend, we'll just focus on the main group element. I won't question you for periodic trend of the transition metals because they're more complicated. So in these several trends, the ionization energy and then the atomic radii, these two are more qualitative. We have equations corresponding to how to estimate these trends. The electron affinity and electron negativity are more qualitative. I'll have the table ready for you in the annotated note as well. All right, and next lecture we'll start talking about chemical bonds.